So from a conceptual point of view, this video is probably going to be one of the most important videos of Calculus 1. It's so important because this is the video we talk about the underpinnings of the derivative, how the derivative is constructed technically. So let us begin. As usual, we'll draw our y-axis and x-axis. And we're going to draw a function, and what we want to do is get the derivative of this function at a point. Derivative, remember, is the slope or steepness of a curve at a point. So let's produce a curve. Here's a curve, and we'll give it a name, f of x. Whatever the x-coordinate is, we find the y-coordinate by inputting the x-coordinate into the function. Okay. So where are we going to get the derivative? Let's pick a point. How about right here? Looks kind of steep right here. Of course, as the curve progresses, the steepness or slope decreases. But right here is we're going to have a certain slope. How do we get the slope of the curve at a point? Well, you've seen in previous videos that I talked about drawing a line which hits the curve at one point. That line has a name. It's called the tangent line. So there, I've produced a line that hits the curve at a point, and this line is the best approximation to the curve at this particular point. So getting the slope of this line, we can use the slope of that line to then define the slope of the curve at that point. You see, if this were a ski hill and gravity was in reverse and we skied up this, our skis would be pointing in this direction at this point. Okay, so the slope of our skis, the steepness of our skis, would represent the steepness of the curve at the point. So the tangent line can be the representative of the curve at that particular point. At any rate, so here's the tangent line. I'll abbreviate, call it the tan line. And I would love to get the slope of this tangent line. I really would. However, if you've seen my video on slope or anybody's video on slope, you know that we need 2 points to construct the slope of a line. Alas, we only have 1 point. And I'll give this point a name. I'll give the x-coordinate a name, x naught. And because x naught is on the function, the y-coordinate would then be f of x naught. Okay, so I'll write those coordinates as a pair, x naught, f of x naught. Fabulous. So how are we supposed to get the slope of the tangent line? Well, here's what we do. We pick a second point on the x-axis that's not too far away. Well, we're going to look at this under a magnifying glass. So if we want a point that's not too far away from x naught, maybe we'll add a little bit to it. And I'll give that little bit a name, h. So we'll call this new x-coordinate x naught plus h. Okay? What are we going to do with this new x-coordinate that's nearby? Well, we're going to find out what the y value is and find out what x naught plus h is when we lift it up to the curve by computing the function value. In other words, we're going to have a new coordinate. The new coordinate is going to be x naught plus h, and then f of x naught plus h. Okay, great. So now we have a second point. Well, what we can do with that second point now is construct a line from the original point. And remember, this is where we want to find the slope. We want to find the slope of this tangent line, which will give us the slope of the curve at this point. But as I said, we only have 1 point on the tangent line. So we'll construct a new line between these 2 points. Well, this new line has a name called the secant line. Okay, so there's good news and bad news about the secant line. The good news about the secant line is we can construct the slope of the secant line by taking the change of y over the change of x. The bad news is that the secant line is not the tangent line. Well, we're going to fix that. We're going to show a way that we can technically move the secant line so it coincides with the tangent line. But first, let's write down the slope of the secant line. So here we go. M, and now to indicate that it's the slope of the secant line, I'll call it m sec. That's just a name, okay? And we're going to take the change of y. So here's the y coordinates. So the change of y is f of x naught plus h minus f of x naught over the change of x. So the change of x is going to be x naught plus h minus x naught. X naught plus h minus x naught. Well, if you're looking closely, you can see that the x naughts are going to cancel, so the slope of the secant line can be written a little bit nicer. It can be written as f of x naught plus h minus f of x naught all over h. Now, as I said before, we're going to move the secant line by taking the limit as h goes to 0. So this is the slope of the secant line, boom. And if I take the limit, which just makes h get smaller and smaller and smaller, we have the limit definition of the derivative, which we denote with a prime. So we say f prime of x naught is equal to the limit of f of x naught minus f of x naught plus h minus f of x naught all over h. The limit as h goes to 0. See what's happening? The slope of the secant line here, the limit operation, zoop, moves it so it's coincident with the tangent line. And that's the inner workings of the derivative.